In our last video, we examined how to partition the sum of squares into the sum of squares within groups and the sum of squares between groups. In this video, we're going to see how to use those sum of squares to calculate the F statistic. Now, previously, we noted that to calculate F, we divide the variance between groups by the variance within groups. And to calculate the variance between and the variance within, we need the sum of squares between and the sum of squares within, as well as the degrees of freedom between and the degrees of freedom within. Partitioning the sum of squares showed us how to calculate the sum of squares between and the sum of squares within, these two numbers here in blue. I know that was a lot of work for two numbers, but the rest of the calculations are pretty straightforward from here. Our next step is to determine the degrees of freedom between and the degrees of freedom within so that we can then calculate our variances. All right? Let's go. Now, we'll begin by revisiting the formula for the partition sum of squares. The sum of squares total is the sum of everybody's square deviation from the grand mean, right? That's just our old regular sum of squares formula using a grand mean because we have multiple groups. And we know that the degrees of freedom in this case is just n minus 1, right? So the total degrees of freedom is equal to n minus 1. Now, what about the sum of squares between? That was y bar minus y double bar for each person, then squared and added up, right? Now, so far we've talked about degrees of freedom being equal to the number of people minus 1. But with the sum of squares between, we're looking at group means, not individuals. We have some number of groups, we'll call that K, and we're looking at the differences between those group means and the grand mean. So our degrees of freedom between is equal to the number of groups minus 1, or K minus 1. All right? And finally, we have the sum of squares within. That was y sub I minus y bar for each person, and squared and all added up, right? Now, again, remember that we have k different groups. And within each of those groups, the degrees of freedom would be equal to the n for that group minus 1. So we have the n for group 1 minus 1, and the n for group 2 minus 1, and the n for group 3 minus 1, and all the way up to the n for group k, remember we have k groups, minus 1, right? So when we add up all of those n minus 1s, it's the total n minus 1 for each of the k groups, or n minus k. So the degrees of freedom within is equal to n minus k. Now, if you look at that for a moment, you'll notice that the degrees of freedom within is equal to n minus k, and the degrees of freedom between is equal to k minus 1. And if we add n minus k and k minus 1, we get n minus 1, which is our total degrees of freedom. Pretty cool. We've partitioned the total degrees of freedom into the degrees of freedom between and the degrees of freedom within, just like we partitioned the total sum of squares into the sum of squares between and the sum of squares within. Okay, so that gives us our degrees of freedom between and the degrees of freedom within. Great. We now use that information to calculate our variance between groups and our variance within groups. Now, this is very straightforward. We calculate the variance between groups simply by dividing the sum of squares between by the degrees of freedom between. And we calculate the variance within groups simply by dividing the sum of squares within by the degrees of freedom within. Like I said, very straightforward and simple at this point. So that gives us our variance between and our variance within. We are almost there. We now use those two variances to calculate our F statistic, okay? And that's easy at this point. F is just the variance between divided by the variance within. You can't get much more straightforward than that. Now, F scores follow an F distribution, just like Z-scores followed a Z-distribution, the normal curve, and T-scores followed a T-distribution. And remember how the shape of the T-distribution varied based on our degrees of freedom, kind of how thick it was out in those tails. The same thing applies here with a little twist. Now we have two types of degrees of freedom, the degrees of freedom between and the degrees of freedom within. So reflecting that, the shape of the F distribution varies based on both the degrees of freedom between, k minus 1, and the degrees of freedom within, n minus k. So what does the F distribution look like? In general, it typically looks something like this. Now, as an illustration, here is the F distribution based on 3 degrees of freedom between and 96 degrees of freedom within. Now, notice how we report F. It's similar to how we report T-scores, where we had T, then parentheses with the degrees of freedom in the parentheses. Same thing here. It's F followed by parentheses with the degrees of freedom between, comma, then the degrees of freedom within in those parentheses. You always list the degrees of freedom in parentheses with the degrees of freedom between first, followed by the degrees of freedom within. All right? Now, a few points. Notice that the degrees of freedom tell us a couple things here. Again, in this illustration. For example, it tells us that we have 4 groups. Do you see that? See why? Well, remember, the degrees of freedom between is equal to the number of groups minus 1. So 4 groups minus 1 gives us the 3 degrees of freedom. We got 4 groups. The degrees of freedom also tell us that for this illustration, the total n across all of the groups is equal to 100. Do you see that one? That's because the degrees of freedom between, 3, plus the degrees of freedom within, 96, equals 99, which is the total degrees of freedom. And remember, the total degrees of freedom is equal to n minus 1, or 100 minus 1. Our total sample size is 100. Great. And while we're at it, also remember that F can't be negative because it's one variance divided by another variance. Given variances are squared values, they must be positive. And as we discussed previously, if the null is true, we expect to get an F somewhere around 1, because in that case it would just be one estimate of sigma squared divided by another estimate of that same sigma squared. And don't forget, this distribution reflects the values of F that we would expect to see if the null hypothesis is true, right? Because even if the null is true and the means in those different populations are all the same, we wouldn't expect our sample means to be exactly equal. There'll be some random variation. The larger the F, the less likely it is that we would have randomly stumbled on samples with means that are that different if the null were true and the population means really are all the same. So let me be clear. The larger the F, the less likely it is that the null is true. So just like with the z-test and the t-test, the question now is whether the F is so large that it indicates the probability of the null being true is smaller than our alpha level, in which case we can reject the null. If alpha is 0.05, this translates to whether the probability of getting an F as large or larger than what we observed in our study is less than 0.05. Now, how big does F need to be to reject the null? What's that critical score, that line in the sand? Well, again, because the shape of the F distribution varies based on the degrees of freedom, it depends on the degrees of freedom. In this case, with 3 and 96 degrees of freedom, if alpha is 0.05, the critical F we need is equal to 2.699. The area above an F of 2.699 is equal to 0.05 or 5%. If F is greater than 2.699, you reject the null. If it's not, you fail to reject. Now, to get the area above the F that you obtained in your study, just use a table or a calculator or some other method to find that area for your F score based on the correct degrees of freedom. That area above the F score you obtained in your study is your p-value. In this case, without even looking it up, we know that if your F is greater than 2.699, your p-value will be less than 0.05 and you'll reject the null. If your F is less than 2.699, your p-value is going to be greater than 0.05 and you'll fail to reject the null, right? Now, with that, let's wrap up this video. Next, we'll actually go through the entire process of hypothesis testing using a one-way ANOVA, from generating your hypotheses to calculating F by hand to making your conclusions. All right? See you then.